In this demonstration, we are going to show how to use VMAP plugin for HyperMesh to analyze vibration test data and also perform correlation with finite element analysis. To give some description of the experiment, it's an experiment performed on a cantilever beam which is fixed at one end, and impact test was performed. So the beam was given an impact input with a hammer, and triaxial accelerometers were mounted at multiple locations, and response signals were collected. Now, with this data being available in the database, how do we bring up this data within HyperMesh using VMAP plugin, and how do we analyze this data? Also, we will show how to import finite element analysis models within HyperMesh, and how do you perform correlation using VMAP plugin between test data and finite element analysis results. We launch HyperMesh. So in this computer, we already have VMAP plugin installed. So the way I bring it up is go to Utility, click on VMAP. So here, these are arranged in the order of the workflow. I'll skip data collection. Instead, data collection has been already performed and data is available in the database. So here I've already organized the data into finite element result files and test data. This will bring up the geometry. So what we are seeing here is a virtual prototype of a cantilever beam where these 7 dots marked in yellow represent the 7 locations where triaxial accelerometers were mounted to collect vibration response data. And at this location, we were impacting the beam with an instrumented impact hammer. The first step is to import data. So for that, we need to go to the folder where the data is available. Click OK. Now, we can look at the various test data that is available in the database by clicking on VMAP graph. So these 7 nodes refer to these 7 nodes on this beam where the sensor was mounted and data was acquired. So for default, we are seeing the mode indicator function, which shows these red points essentially are the resonant peaks. If you want to add additional modes to this, we can do that. So let me start with time series. This is stimulus and response signal. This is stimulus and response. You can see one node at a time or all of them or more than one. You can look at FFT of the stimulus, FFT of response, FRF amplitude and FRF phase. You can look at coherence, overlap these graphs just to check if the signal to noise ratio is good, near resonances especially. You can see that the coherence drops wherever there is a 0. And coherence is in a log scale, so 0 would mean the highest value, which is expected near the resonances. Now, having seen these graphs, we want to create result files to generate the data that is required to see a visualization of the mode shapes. So in this graph, we can see that there is one resonance right here, 2, 3, 4, 5, and so on. These result files are for seeing what we can also refer to as ODS, corresponding to resonant frequencies, operating deflection shapes. So all I need to do is go near the resonance and make a result file. Result file at mode 17.5 Hertz was successfully created. We want to create a result file corresponding to this. I can make other frequencies also, but I'm interested in visualization of mode shapes corresponding to resonant frequencies. So I'll pick this. We can create a result file.